I want to talk about the lessons we've learned at ThingCell while we ported our software from Windows to macOS and in little parts to the web. So what's the problem that we started with? We had been doing about 12 years of development only for Windows when we decided we wanted to port our software to macOS. And in those 12 years, we had written about 1 million lines of C++ code. And you can imagine that we had used Windows APIs, Windows data types throughout our entire code base, everywhere. So there was, first of all, quite a lot of cleanup that we had to do. What's special in our case is that our product is an add-in, which is dynamically loaded in PowerPoint and Excel. And that has some important implications. It means that we are not in control of the main application. And unlike people who do server development, we are not in control of the computer either, of course. Some of the implications are that we have to be very flexible regarding a lot of things because so many things are out of our control. For example, we have to be able to render into anything that PowerPoint or Excel would give us as a backing surface. We have to be able to render into views or core animation layers on macOS, or H windows or DirectX textures on Windows. We always needed a renderer that would support DirectX on Windows and OpenGL on the Mac, just because that's what our host application did, and that's what we felt was best supported. Of course, we share the main message, the main event loop with the application. We don't control that either. And we always wanted to support platform-specific features, the same ones that our host application would support. That could mean small things. For example, on the Mac, there's this triple-click feature. So if you triple-click text, the entire paragraph is selected. So if our host application would support that, then we would have to support that too, just to minimize the friction in using both parts of the application. But it can also mean bigger things. For example, on macOS, Office runs in a sandboxed environment, and that means we are sandboxed too, and we had to live with that. And of course, when we started porting ThingCell, we were looking for some cross-platform toolkit that would just hide all those platform specifics and would simply behave identically on all platforms. And this talk is largely about why this does not exist and why this cannot exist, actually. I will go over several of the challenges that we faced while we ported ThingCell. Some have more code than others. First of all, I want to start talking about one of the most important problems that you face when you start porting your software. You have to find the right level of abstraction. At what abstraction level do you hide the inevitable platform-specific code that you will have? So you have your operating system on one end. That has some features. Every operating system is a bit different. And you have your platform-independent C++ world that doesn't know anything about operating systems. And then at some point, those two have to meet. And how does that boundary look like? Is that just the C++ standard, or do you have to write something special that is special for your application? And well, how that boundary looks like is very much special, and it depends on your application, and it depends on the semantics of your code. It really depends on what it is you want and what it is you need, and there's no single correct solution. When I looked through our code base and looked at things where we developed cross-platform abstractions, there were a couple of easy cases where the semantics were so clear that it was really a no-brainer how to program that. So one example, for example, is the rendering engine, where we have our internal rendering that produces lists of triangles with texture coordinates. And then we pass that to some rendering engine. And that rendering engine is completely platform specific. But from the viewpoint of the C++ programmer, we don't care. We just give triangles to some interface. What happens behind that doesn't really matter. One backend produces DirectX commands, the other OpenGL commands. So it's a simple interface. Another simple case was doing HTTP requests. When we do HTTP requests for downloading updates or whatever, we are using the system APIs always. So we don't use by default cross-platform APIs like CR or something. because we want to use the system APIs where we are sure that they use the system settings, for example, for proxies that the user might have configured. So we have a business software, IT departments configure a lot of stuff. We want to make sure we use the most default solution we can. So all those system proxy settings, firewalls, whatever, are used correctly when they are configured. Here again, the interface is super simple. I mean, you have a URL you want to access, maybe with some arguments, and you get data back. That interface is essentially a function with some data in, data out. And a slightly more complicated, but also relatively simple example is starting child processes. Also, the implementation can be very different. Starting child processes, maybe it's running in a sandbox environment, and maybe you want to set up some I/O mechanism between the child and the parent process. But also that can also be abstracted away nicely, where you don't really care about the implementation, as long as you get something back that represents a child process that you can send data to. So what all these three cases have in common is that they have very clearly defined data in and data out. And what happens in between can be a complete black box from the viewpoint of the programmer. The more interesting case are the cases where you really have to interact with operating system objects. And a very simple operating object is, of course, a file. So let's look at a very simple example, probably something everybody has tried to do once. That's how to rename a file. So when you want to rename a file, there are different options that the operating systems give us. So in Windows, we have the moveFileX function, which of course takes the original file name, it takes the new file name, and it takes some flags. I've omitted some flags here, but the important ones is that you can tell moveFileX that it can copy the file when the source and target are on different volumes, and that it is allowed to override the target file if it already exists. By default, it wouldn't do so, it would return an error. On Linux and macOS, there are different functions. There are two versions of the rename function that have different options, of course. So one of them is not supported by Windows. The rename functions can swap the source and target file atomically, but only on supported file systems, whichever those may be. And then it has an option which also exists on Windows, where it says, okay, I can return an error if the destination file already exists, but also only on supported file systems. And last but not least, macOS has something else entirely. The copy file function also takes the source file name, the target file name. It can report in progress state, and it also has different flags. For example, and very interestingly, you can specify if you want to copy the access control list of your file from the source to the target location, or if you only want to copy the data. And well, you can think, I have operating systems that support access control lists. That's a valid question. Do I want the access control list to be copied or moved with the file, or don't I? But the other one didn't let me specify that. So you can choose copy the ACL, copy the data, copy both. You can also fail if the target file already exists. The others could do that too. And you can move the file in the sense that you remove the source location. It's unclear if that's an atomic move or if it's not an atomic move. So here we have many options on the operating systems, and it's not clear how the common denominator of all these options would look like. What is it actually that we can do on all of those operating systems? How does the common interface to those operating systems should look like? And well, we actually have an answer. The C++ standard gives us an answer. That's the answer. It's a simple function that returns no errors. It always overrides the target and does give us no options at all. And I would argue, if that wasn't bad enough, it also implements the least useful semantics they could come up with, because overriding the target file is something that I never wanted to do. And I know why they did it, because that's what the POSIX standard actually standardizes, also a very useless function. But I don't see how that function can ever be used in production software. So I think we need something better. And I think we always need to do something better. But how does better look like? And how do we make a better cross-platform rename function without filling our code with if-defs and different flags on different operating systems. It's pretty hard, apparently. It's pretty hard to get identical and useful semantics on such a low level. And rename is a very low-level function. And I would say, well, luckily, that's actually not the problem we have to solve. We don't need a cross-platform file rename function. That's the wrong level of abstraction. We need to raise the level of abstraction, and the problem becomes much easier. If you look at what your application really needs to do in the places where you wanted to use rename, there are a couple of different things that we wanted to do. For example, we wanted to download a file to a cache in a thread-safe way, where we downloaded it into some temporary file with a random name. And then when the download was done, we wanted to rename it to the actual cache name in some atomic way. So no two processes that would cache the same file would ever override the same cache location. Maybe we wanted to create a user application settings file, or we wanted to create a temporary file that is automatically deleted, but which can be opened by different applications at the same time. Or we wanted to create a document in a user-specified folder, which would involve opening a system-specific save file dialog, creating a sandbox exception, etc. So there were a lot of file operations we needed to do that had much stronger semantics than just renaming a file. And it's those stronger semantics that we can actually implement in identical and useful ways on different operating systems. So let's look at two examples. The first is the simplest example, how to create a settings file that is user-specific for your application. So on Windows, we would say, well, we probably want to store that settings file in the app data system folder, in a ThingCell subfolder. That already implies a choice that only Windows makes us do. The app data folder, the application data folder, is what's called roaming. That means that if your user profile is stored on a server, it will be copied to every computer you log onto. And this ThingCell app data folder will also be copied. That's useful. If people use our application and use different computers, we probably want them to use the same application settings on each of those computers. Then on Windows, a process can run under the same user, but with different integrity levels, which is also kind of privilege. So a process might be started with a high integrity level, then it stores some settings files, then it's run under a lower integrity level, and it maybe cannot read the settings files the process has previously written. So maybe we want to encode the integrity level in the folder name as well. And then we're done. macOS offers us different choices, and we have to do different choices. On macOS, maybe the standard location would be library application support ThingCell. But maybe our application is running in a sandboxed environment. And maybe we know that there is a group of applications that we have written that should share the same sandbox, and they should share the same access to the same files. In that case, there would be one location, a group container, a so-called group container, that they could all access. And maybe we want to store the settings there. And then last but not least, because we know what the semantics of that function is, there are a couple of decisions we can make, which we always make identically, because we know what we're supposed to do. For example, we could say, well, when we are writing that user settings file, we always obtain an exclusive lock while we are writing that file. And we also always want to inherit the access controllers from the parent folder when we create that file, because the parent folder is a system location, and we assume it has the correct access controllers set. So in that sense, there are a lot of decisions we can make here, different decisions that are different on each operating system and decisions that are identical on different operating systems, just because we know what we are supposed to do. So a more complicated problem is how to create a temporary file that will be automatically cleaned up for us, but which can be opened by another application in the meantime. So on Windows, that is pretty easy. You can create a file with create file, you give it some location in the temp folder, then you specify some Windows-specific settings, some security attributes. Maybe you want to prevent file execution. You want to make the file accessible by the current user. And then on Windows, there's this magic flag, file flag delete on close, which does exactly what we want here. It says, well, when the last handle to that file is closed, then Windows will take care to delete that file automatically. But in the meantime, everybody who has the path or a handle to the file can read from that file. So that's pretty useful. There's no such thing on POSIX systems, unfortunately. So we have to do something ourselves. So we open the file. Here, I assume it's in the group containers folder because I said we want to share the settings file or the file with different applications. Again, we make the file readable and writable just for the current user. And then there are a couple of macOS-specific things we have to do, or POSIX-specific things. The open call can be interrupted by a signal, and we have to handle that interrupt and maybe try the open again. And then we have to do the cleanup ourselves in some way that is conformant with the desired semantics. So maybe we want to implement reference counting in some shared memory object. We can't do the usual POSIX temp file trick here, which is to create a file and then delete it immediately, because I said we want it to be readable by different applications at the same time. Maybe we say, oh, manual reference counting in shared memory, that is error prone. If our application crashes, then we have no guarantee that we actually cleaned up the file. So let's do something simpler. Again, we know what the semantics is. We're not writing some low-level meaningless function. We know pretty well what the use case is. So we are very free in the choice of our application. And we can decide, okay, we can do something completely different here. We can, for example, say, well, let's store all the data, all the temp files that have this requirement in some database, in a single one, and just hand out objects that look like files that can write into that SQLite database. And now maybe we are crashing, and maybe that database stays around on the disk, but now we only have one file to clean up whenever we start again. So that simplifies our cleanup problem at the very least. So that shows the advantage. You can choose very different implementations because then you know the contract that the function is supposed to fulfill. So that's why we're saying that what we found was that cross-platform interfaces need to have well-defined and strong semantics. Otherwise, it's impossible to implement them correctly. If your cross-platform interface, your abstraction level, has a too weak semantics, then there's a good sign that you've created a problem is when you start to look at the implementation on one of your operating systems. Because you know your operating system, you know the questions it's going to ask. Do we lock the file? Do we copy ACLs? Do we create the correct security descriptor? And you notice your function interface does not seem to imply the correct choice here. So it's not clear what happens on one operating system. And you start digging into the implementation. That's when you know you've made a mistake in your interface design. And as I've shown before, specifying strong semantics increases the degree of freedom for your implementer, which is a good thing. When you're choosing the right level of abstraction in implementation, there are essentially two mistakes you can still make. You can introduce that level of abstraction from your operating system at a too high level. That would mean you miss a chance to unify some code. In my experience, that is extremely rare. I don't think I've ever made that mistake because we are very lazy as programmers. But I've done the opposite mistake quite a lot of times. I've tried to force common interfaces on too low-level things, like file rename, for example. And that either means that you lose all the expressiveness. So we've seen what the C++ standard made of all our powerful operating system-specific rename functions. None of that power was left in the standard function. Or you implement something that kind of works, but whose semantics don't match one of your operating systems very well. One example I found was, for example, qfile set permissions. If you're not familiar with that, uses the POSIX permission model on Windows as well. So qfile set permissions on Windows lets you specify the readable, writable, executable bit for user group other on Windows files. And you can certainly implement that on Windows because the Windows security model is very powerful, but it just does not match the Windows security model. So in that sense, it doesn't match your operating system. So that's the first part of my talk. In the next part, I want to talk about something else we found, that sometimes you just get given objects by the operating system that behave very differently. And that's also something that you sometimes have to deal with, and that cross-platform toolkits don't solve for you. That's a problem that they don't solve for you. We use shared memory a lot in our application to implement inter-process communication. And I've said initially that our product is an add-in, but that's not the entire story. So our product is an add-in which runs in PowerPoint and Excel. Those two already have to communicate with each other, but there are quite a lot of other processes involved. We have a Google Chrome add-in in the little web app that lets you link data from the Tableau.com data tool for ThingCell charts. We have processes that do OAuth authentication, so users can import images, for example, from Getty or other image databases. We have a chart scanner that uses text and image recognition techniques to extract data from charts that you would just have in a PDF report. So you can essentially take the screenshot and it will try to read the chart and then get data out of it and put that data in an Excel sheet. And we also have a command line tool that lets you batch create presentations from a template and data that you give in JSON file format. And then you can create your monthly reports in PowerPoint. So all these tools have to communicate with each other, and they use inter-process communication for that. So they use shared memory for that IPC. We use Boost Inter-Process because it does offer a common API for shared memory on Windows and POSIX. And it offers everything that you need, essentially. So there's a shared memory object, a named memory object that you can map into different processes and that you can look up by name. And there's a special kind of shared memory pointer. So you have the shared memory segment. You map that into each process, but it will be mapped at different addresses. Now, if you want to store a pointer in that shared memory to another address in that shared memory, let's say you want to store a vector of things. That vector internally has 3 pointers, but it can't be raw pointers because then the vector would not be correct in the second process that has mapped the shared memory. Instead, the vector should use offset pointer, which uses a clever trick. It stores an offset to its own dis pointer. So the offset pointer is correct in all processes that map the shared memory object. And last but not least, you need some synchronization objects. So you can synchronize access to the shared memory object. And how does that look? Well, it looks a bit like this in a very simple example. Here, I have a server process that creates some shared memory object with a given name. That name has to be very specific. Maybe the shared memory object lives in some global namespace. So it should be specific to your software version, maybe your host, maybe your security identifier. And then when I have that shared memory object, I can construct an object by name, here a simple pair of double init. And then in my child process, I can look up that object by its name, that shared memory object. And it will be mapped in my process, and I can look for the pair and I find it. Now let's say I run those two processes and they terminate. And I start the server process again. Well, what happens? To my surprise, I will get an error here. And the error will say a shared memory object with that name already exists. And that's kind of surprising, isn't it? It's especially surprising if you're coming from Windows. Because it means Boost Inter-Process by default does not use the Windows shared memory implementation. That would look like this. On Windows, shared memory is essentially an anonymous file mapping. So you can create a file mapping that doesn't map any specific file, but instead it will be mapped by the page file. Now again, we can map that same object in different processes. And when all these processes have died, then Windows will clean up that shared memory object for us. And if we recreate it, we get a fresh one that is uninitialized. That's great. That's a great guarantee. Windows cleans up after us. Good guarantee. We never get stale shared memory. That's a feature that we want. But it's not supported on POSIX. POSIX shared memory works differently, and that creates a lot of problems over the years. So when I first encountered that, I started Googling for a solution. And all I found were people who had the same problem. Everything, I have to clean up everything myself. How does that work? So on Windows, generally, kernel objects, shared memory, mutexes, even the temp files we've seen, are reference counted. That means when the last user or the last process that used them has died, even if it has crashed, the resource is freed for us. On POSIX, shared memory can be either file-backed, which means the backing file still exists if the processes crash, even after a system reboot, or it can use the actual POSIX shared memory implementation, but that is very limited on many POSIX versions. And it still means that the backing memory will persist when our processes has crashed, until the reboot at least. So here POSIX assumes a server-client model where the server owns the shared memory object, and it has to take care that when the server started first, it cleans up the old one and creates a new memory object. If that's not your process model, and it wasn't ours, then I could find 1.5, 2 solutions to that problem, but neither Boost Interprocess nor Qt implemented them. So one solution, or maybe only half a solution to the problem, were robust mutexes. So a pthread mutex can be marked as shared, process shared. That means you can store the pthread mutex in shared memory itself. And then you can also mark it as robust. And a robust pthread mutex keeps track of which process last locked it. So if you try to lock the mutex and the last owner of the lock has died while it held the lock, then pthread mutex will return eowner dead and tell you so and say, oh. And then you know that the resource you're guarding, the shared memory object in our case, is probably in an undefined state. And you have to clean it up, or you have to terminate, or whatever. So that's half a solution, because it doesn't tell you anything if the other process has died while it did not hold the lock. And you might also want to clean up, but you will never know. So macOS, well, there's a Boost Interprocess pull request by somebody who wants to get that merged to Boost Interprocess, and that maybe needs some support because it hasn't happened yet. macOS didn't support robust pthread mutexes anyway, so I had to look for another solution. The only other solution I could find was file locking, because file logs are the only resource that have process lifetime on POSIX systems. And there's a big warning here, because file logs are very weird on POSIX systems as well. And there are a lot of things you have to watch out for. And there's also a Boost Interprocess pull request by us. Because what did we do? We introduced a different kind of shared memory object. And in its most internal method, the details are not so important, we also create a backing file. And in that function, we create our backing file. We try to obtain an exclusive lock to that backing file. When that succeeds, then we know we are the first ones, the first process to open that backing file, to open that shared memory object, and we truncate the file. So we try to do the same that Windows does and guarantee that you always get a fresh shared memory object. And once we have truncated the file, we degrade our exclusive lock to a shared lock and go on with our lives. When obtaining the original exclusive lock failed immediately, we know we're not the first ones, and we just wait until we get a shared lock. So that sounds super simple and has worked well in practice, and I think gives much better semantics than the default implementation. It has 2 small problems that I think are not actually problems. The one problem is that this flock call down here, where it said it degrades the exclusive lock to a shared lock, is not actually an atomic operation. It actually releases the exclusive lock and then waits for a shared lock. So that can be a problem, but it is not a problem in our case, because there are only 2 things. While that flock case call has released its exclusive lock, that open might succeed with an exclusive lock, and the second process might think he's the first one. In that case, that other process will also truncate the file, but truncating the file twice is luckily not a problem. And then both will go on with a shared lock. And the second thing that can happen is even more harmless, is that this call would succeed before that call succeeds, and that doesn't matter. More interesting problem is that, as I've said before, file locks on POSIX systems are difficult. And one such problem is what happens if you want to obtain a file lock to a file that is stored on a network file system. And here also we are, I think, lucky, and all that we require here is that these file locks are visible on your local computer. They don't actually have to be visible on other computers that have the same drive mounted. So there's also boost inter-process pull request by us, because I think that's useful semantics for a shared memory object. Maybe you can give that an upvote. So here in that chapter, I wanted to say that, again, in our cross-platform development, we were aiming for strong and identical semantics for all our kinds of objects. And strong semantics can also mean strong guarantees. And it especially means strong guarantees from your operating system. These are almost always good. And here, what the Boost implementation did, it sacrificed operating system guarantees on one operating system for the sake of an identical API. And I understand why they did that, because one was easier to implement on the other operating system than the other way around. But that doesn't mean that that solution is the right one for you or the right one for everybody. Here there were problems. Maybe it's a problem. Maybe network file systems are more of a problem in your use case than in our use case. So there might be different, different considerations here. But in our case, we found that we could actually implement better semantics when we looked at the problem and we looked at the requirements that we had. We know our constraints, I say on the slide. So that's something that you might be able to do better than even cross-platform toolkits can. So now I want to change focus a little bit and talk more about actual tools that we have built, and some of them are also open source. The first tool we've built is very much C++, unlike the previous two chapters maybe. And it concerns text internationalization. Text internationalization in general is more than just translation, but here I focus on text translation. So how does that usually work? Well, every text translation toolkit has to have three features. The first one is that you want to annotate the text that should be translatable in your source code so that you can easily extract it and send it to the translators. The second is that all those translations, they need a context for the translator, so they know what you are actually talking about. And last but not least, your translation software must not make many assumptions about properties of your language, because languages are very different. And I learned when I prepared that talk for, I think, CPP Russia originally, that Russian has a different number of plural forms, for example, than English or German has. When you have such a tool, then the usual flow is always the workflow is always the same. So you have your annotated source code. You extract all the translatable text. You send that to the translators. Then you get something back in XLIF file format, in that XML localization interchange file format. You import that into your project somehow as a resource. And then at program runtime, you would look up the original text, let's say in English, plus your current UI language, and you get the correct translation back. Now that's a problem where you do not want to support different native mechanisms, because that would be horrible. You want to have the same markup in your entire code base. You also want to have a single text extraction run that will find all the translatable text, regardless of which platform they will run on in the end. And at runtime, you also want a uniform way to access the translatable text. You don't want to have cases where some calls return a reference counted in a string pointer, and some calls return a basic string that is heap allocated. So it should work the same in all cases. Boost Locale does that for you, for example. Boost Locale did not exist when we started to translate our software, but it does everything that I've just described. There's a translate function, which also serves as markup. The translate function supports translation context. Here I want to translate open in the context of opening a file to German. And it supports, for example, different plural forms in Russian. And then that translate function also does what I just said. It will, in the background, do a runtime lookup in its translation catalog and return the correct translation. But this is not 1995. We don't have to do runtime lookups. We have const_expr functions now, and we can do compile time lookups. And that's actually what we do. So you have a very simplified example of our code. Let's say we only support 2 languages, English and Russian. And then a translatable string is just an array of those 2 translations. And the translate function would choose the correct option, considering our current UI language. So that's the translookup macro in that case, unfortunately, is where the magic happens. Given a string and a context, it would return the correct translatable string. And if we have that, then we can put it all together and output a translated string. So what does translookup do if it doesn't do a runtime lookup? Well, it does this. There's a translatable string map, and that's essentially a compile time hash. A compile time hash map that takes 4 unsigned integers as keys. And those unsigned integers are a compile time computed hash of the string and the translation context. You see here we use a murmur hash, and we calculate the hash for the string and the context. And because there's no built-in 128-bit integer type, but the hash will be 128-bit, we split the hash into 2 64-bit unsigned integers. And now if you see that, and if you know C++, you can probably imagine what our translation tool outputs. It outputs template specializations, of course. So our tool, the tool that we have that processes the xlib files that are returned by the translators, will calculate the same murmur hash at build time that we calculate here in the C++ compiler, and will output a CPP file filled with those template specializations. And of course, now you might wonder, why do we do it like that? Well, in a cross-platform environment, this has one big advantage. I don't have to worry about installing files, finding those files on the disk, having IT departments delete the files, having IT departments change file permissions on those files. There's a whole class of problems I no longer have, just because I can look up this translation in our binary at compile time. It makes our binary larger. We also could not ship additional languages in some language pack that would be dynamically loaded, but I don't know who still does that anyway. So a short reminder, what can const_expr functions do? Well, they can do a lot with literal types. A literal type can be a scalar, can be a reference. Aggregate types that you can initialize with brace initialization are literal types, for example, a std array. Types that have const_expr constructors and destructors, and literal data members and base classes are literal types themselves, for example, pair. And all arrays of literal types are literal types. Now, const_expr functions, of course, can't be virtual. They cannot contain goto, and I think for now they can't contain try-catch statements, but they can contain if, switch, and all loop statements, which makes them very powerful and very easy to use. And they can use local variables as long as these are initialized and literal type themselves. So all that is easily enough to essentially take the hash implementation that is open source and implement it in a const_expr context. So here you see the implementation. It contains a template on the length of the string. We even take the pointer to the first element of the string as a car pointer, and that is also not a problem in a const_expr context. And I spare you the implementation because that's easily found online. So here, looking for strong and identical semantics means we also want to have, as far as possible, the same tools in our build process. Tools that are, that produce the same output, of course. And the first version of my talk, that's left here for some reason, I kept score of which operating system did something better than the other one. So we at ThinkCell, we also do pretty special error reporting. We've given entire talks on our approach to error reporting, and this is just a short excerpt here, because it also had very important implications in a cross-platform context. We have a very powerful error reporting architecture, and we use a lot of asserts in our code to check invariants. And what's special at ThingCell is that those asserts stay in the code even in release builds. We also check all return values from all system API calls we do, and we always distinguish between expected and unexpected errors. So if you try to open a file, then it's always an expected error that the file no longer exists. But it would be very unexpected if the function suddenly returned error out of paper. So you have to handle the file does not exist error. You do not have to handle the error out of paper error. You just can assume that it will not happen, and we will report an error if it does happen. So once we encounter an unexpected error, like error out of paper, then of course we must show an error message. But more importantly, we send an error report home to our backend server. And that server will analyze the error report. It can, for example, check if we have already fixed the bug, or if we need more information from the user. It will report that back to the process that has just encountered that error. And that process can then decide to download the available update silently and even install it silently. And it can even reload our add-in silently. So the entire process might be unnoticeable by the user, but we will fix the problem and it will never occur again. Or it might, well, if the backend decided we need more information, then it might show a more helpful error message to the user saying, could you help us reproduce the problem, etc. From our developer side, we have a little interface to the database where we can look at the most frequent errors. We can filter them by version, by operating system, etc. And then say, okay, I fixed that in release so-and-so. And that backend looks at the stack where the problem occurred and groups them and filters them somehow, etc. So that's extremely useful, and it finds a lot of bugs that are dependent on the user's setup. Bugs that only occur if you have another software installed, if you have a security tool installed, etc. And the core of that functionality is something that only exists on Windows. It's mini-dump, write-dump, which, as the name implies, is a function that will write a dump of your program. At the very least, a dump that includes the full stack and the registers. And that's extremely helpful information. Microsoft provides symbol servers for all the symbol libraries. You have the symbols for your own software. And together you can symbolicate a dump that maybe takes 100 kilobyte. And you get the full stack of your program at the point where the bug occurred. And you can find out something about the problem. Nothing similar existed on macOS. There's Google Breakpad, Google Crashpad, of course. But again, that's a bit a case of, well, there were pre-existing solutions, but we at ThingCell always like to look at those solutions and see if they are really a good fit. And here, Google Breakpad and Google Crashpad made a lot of strange decisions. So, for example, they write Windows mini-dumps on all systems, even on non-Windows systems. And then, of course, because no tool can read a Windows mini-dump that originates from a macOS system, they need to write custom tools to analyze the Windows mini-dumps. So that was a lot of code for something that wasn't very powerful in the end, and something that we would have to support as soon as we included it in our software. And for macOS, at least, there was a very obvious and much simpler solution, because the macOS binary file format is very well documented, and it includes documentation for the core file format. The situation is a bit different on Linux, where the core file format is not so standardized, I think. But all that we had to do was to write a valid macro core file that would only contain stack memory, and then the standard LLDB debugger could already read it. So this is what we did, and it's pretty straightforward. We've also open sourced the interesting bits of that code, and implementing that was then straightforward, is really going through the file format specification and the list of system calls and assembling the necessary information. The first thing you have to do whenever you write a bug reporting software is that you have to let another process take over. Your process just encountered a problem, an error. It is in an undefined state. Maybe you've overflown your stack and there's nothing you can do. So you send all access rights to some crash reporting process. macOS has a funky kernel architecture. It uses messages a lot, Mach messages. And you can assemble a message that sends all access rights to your process to another process. So we do that. And then we assemble all the important process state. We collect the number of threads, the register state, the memory. We look for overall memory regions, check which memory regions reference stack memory. We include that, and then we write it all out. We write it into a binary file. There are some additional metadata that we need to include. Most importantly, the loaded libraries. The PDB file would include that for us. We have to write it ourselves. So which shared libraries were loaded, what version did the shared library have, and what was its start address. So this is all the information we need. And then our backend can analyze macOS bug reports just as it can analyze Windows bug reports. We have debug builds for our own software. We can cache the system binaries for all the macOS builds that we support because there aren't so many. And then we can write a small driver for LDB that takes all that information and sets it in LDB, and LDB will output a valid stack trace for our crashing process. So that's very good. And again, again, a case where we said, well, we need the same tools on all the operating systems. There are pre-existing solutions that don't quite do what we want, or they're much more complicated than we want them to be, where it was worth our time to implement something ourselves that in the end worked much better for us. So last but not least, a little, I want to whet your appetite, so to speak, for my upcoming CPP Conf talk. As I've said, we've moved some parts of our application to the web. And we ship with a Chrome extension and a small web application. And when we started writing that, it was really our first web application. We had to ask ourselves, well, what language do we want to use? And it was pretty clear that we did not want to use JavaScript because that's just horrible. We started writing the web application in TypeScript. That looked much better. It was type safe. It had awesome type definition libraries that allowed us to interface with legacy JavaScript libraries in a type-safe way. But it turned out that sharing code with C++ was now possible, of course. And there's always a little bit of code that you want to share, even if it's just an enumeration. So we looked at Emscripten. And Emscripten would let us compile C++. So we could share all the code we want. But now suddenly we had the opposite problem. We couldn't interface with JavaScript anymore. Or with the entire DOM object model, for example. That lost all type safety again. Because interfacing with JavaScript looks a bit like in the example down here. It's all untyped checked strings, essentially. You can look up global objects by their name and hope they exist, call functions by name and hope you got the name right and the number of parameters. So that's horrible again. We can't program like that either. So we said, well, maybe we can write our own tool. You see that's a repeating pattern of things that combined the advantages of the TypeScript approach and the Emscripten approach. And we built kind of our own compiler. So I said that TypeScript has awesome type definition libraries. So this is what they look like. This is a TypeScript description of JavaScript, the standard JavaScript document DOM element. So you see, it's the document, and it has a couple of properties. It has a URL. The URL is a string. It's always set. It's never null, but it's read-only. The document also has an active element property, which is an HTML element, but which can also be null. Anchors are a collection of other elements, etc. So the name already says what it is. It's a type-safe description of a JavaScript library in TypeScript. And that is not just available for the standard JavaScript libraries. It's available for over 7,000 JavaScript libraries. So there's a huge repository of such descriptions. And luckily, we don't even have to parse those descriptions ourselves. TypeScript comes with an awesome compiler API. So we can, with that small snippet of code here, we can read a file, a TypeScript file, and iterate over all the syntax known in that TypeScript file and ask, is that syntax node a function declaration? If it is a function declaration, what's the function's name? What is its return type, its arguments, etc.? So we can use that TypeScript parser to parse TypeScript interface definition files and output C++ interfaces. And that's what our TypeScript tool does. So it compiles TypeScript interface declarations to C++ interfaces. So we can call JavaScript libraries from C++ in a type-safe way via Mscript. So when in JavaScript, you would set the document titled property, like here, just assigned to the title property. The C++ looks kind of similar. You get the global document object, and then you call its title setter, and you pass a JavaScript string. But all of that C++ would be compiled to WebAssembly and then would make calls in JavaScript. So this is an example of the code that we would generate, for example. So at the base, there is some JavaScript object. A JavaScript object is essentially an Emscripten value. And if you're not familiar with Emscripten, the Emscripten value just represents a JavaScript object. So when you make a call to Emscripten and tell it to create a new JavaScript object, it will actually call a JavaScript function that will create an empty object, put it in some map, give it a reference count, and then return to the WebAssembly world and say, okay, here you have a handle to that JavaScript object. Do what you want with it. And then we have that C++ version of the interface we've just seen. Earl is just readable, active element is read-only, title can be read and set. And the implementation now looks like the Emscripten calls we have already seen. The implementation is not type-safe. We call the title function by name, and Emscripten will unwrap that name, transform it to a JavaScript name, and then call that property for us. But we have wrapped that in a type-safe interface that we can use from C++. And our project is currently almost self-hosting. That means TypeScript can compile enough of the TypeScript interface definition itself. So we have implemented TypeScript already in C++ that uses this TypeScript compiler interface. And this TypeScript code I've shown before that would parse the program and iterate over syntax nodes would look almost identical in C++. So again, you create a program, a TypeScript program from a TypeScript file that will instantiate the TypeScript parser, and then you can get access to your source file and iterate over all the syntax nodes in your source file. And I'll go over this shortly, and then I think I'll be ready for questions. You can imagine there are quite a lot of challenges when you're trying to parse TypeScript and transform it into valid C++, because those are very different languages. And for example, one of the easier problems to solve is that in TypeScript, the declaration order of your types does not matter. So this is for the TypeScript. I can define a union foobar of two types, foo and bar, that have not been declared at this point. They are declared later, but for TypeScript, that doesn't matter. It would matter for C++. So we have to do something obvious. We have to collect all those types and then sort them and find some order of declarations that will work for C++. There are other problems. TypeScript, for example, supports enumerations that include string values. That's also not supported in C++. And here as well, we do some hopefully clever tricks. We define C++ union, that is a standard C++ union, and then we just specialize the marshalling. So there's some point where the C++ value is marshaled and transformed into a JavaScript value that can be sent to that JavaScript world. And here, the JavaScript value, of course, has to be the string that JavaScript actually expects. There's some interesting magic that I'll skip over here that we have to do to implement function callbacks. Functions, of course, in JavaScript are also just objects that are reference counted. That's something that we can't do here. Our C++ objects always have a scope. They might go out of scope. What do we do with function callbacks? The implementation is not so trivial. And there are a couple of interesting challenges that are still open that we are working on now, that I'm working on now. The first one is generics, which is like TypeScript templates, but they can have interesting constraints where I'm not sure if they'll translate to C++. And then there is one example of the interesting things that TypeScript does to express common JavaScript idioms in a type-safe way. So if you've programmed JavaScript, if you've programmed a web page, then you're probably aware of that standard event listener interface where you call add event listener, for example, on some button. And the type of event that you want to listen to, that you have to pass, is actually a string. So you call add event listener and then click as a string, and then the listener function. So how can you make an interface type-safe that takes the string as a first argument, but you're not allowed to pass any string? And here they did a clever thing. So they said, well, let's define an interface that was never going to instantiate. It's just a description of something. And that add event listener interface is now templated on a type K that is one of the keys of document event map. That means K can be here click or key down the string. So the first argument to type the event listener is either click or key down. And then the listener function receives an event where the event depends on the kind of event we're listening to. And then here they implement a kind of type lookup where they say, okay, document event map of click is a mouse event, and document event map of key down is a keyboard event. So this too is going to be interesting to transform into C++ because it's a very common idiom, but I have some ideas already. Okay, here's the link again. I'm happy if you check it out. I'll have a whole talk on this at CPPCon. And with that, I am done, and I'm open to your questions.